The American people have both the right and the responsibility to know the truth about unidentified aerial phenomena. That truth remains hidden, classified, and silenced by fear, retaliation, stigma, and confusion. Today we are here to help break that silence. Sources close to the Defense Department confirm military officials are seriously considering intercepting the interstellar object 3 Atlas before it changes course toward Earth. Discovery goes on to follow up in characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. The object's bizarre behavior and impossible trajectory toward Mars has triggered protocols normally reserved for incoming asteroid threats. But what happens if we can't stop it? And what if it fights back? The beginning of it all, the story of 3I Atlas, begins with what should have been a routine night at the Catalina Sky Survey in Arizona. On a clear evening in late July 2025, automated telescopes scanning for potentially hazardous asteroids captured images of a faint object moving against the background stars. Initially catalogued as just another piece of space debris, the object's unusual motion patterns quickly caught the attention of astronomers who specialize in tracking objects from beyond our solar system. What made 3 Atlas immediately interesting was its velocity vector. Most objects in our solar system follow predictable orbital patterns around the Sun, but this newcomer was moving too fast and in the wrong direction to be bound by solar gravity. Its hyperbolic trajectory and high speed marked it as only the 3rd confirmed interstellar visitor ever detected by human technology. Previous visitors 2I/Borisov and C/2025 R2 Swan had provided valuable opportunities to study materials from other star systems, making the discovery of another interstellar object a significant scientific event. However, the initial excitement about studying pristine materials from another stellar system quickly gave way to confusion and concern as more observatories around the world began tracking 3 Atlas. The data they collected started revealing characteristics that didn't match anything in the scientific literature. The object's brightness fluctuations, spectroscopic signatures, and motion patterns all suggested something fundamentally different from the natural comets that astronomers had been studying for centuries. The international astronomy community mobilized unprecedented resources to monitor this unusual visitor. Major observatories on 6 continents began coordinated tracking sessions while space-based telescopes adjusted their observation schedules to focus on 3I Atlas. Within weeks, it became clear that this object would either revolutionize our understanding of natural comet behavior or force scientists to consider explanations that challenged basic assumptions about what kinds of objects drift through interstellar space. Industrial materials and deep space. When multiple independent spectroscopic analyses confirmed the presence of refined nickel on the surface of 3I Atlas, the astronomical community faced an unprecedented puzzle. Nickel exists throughout the universe, formed in the cores of massive stars and distributed through space by supernova explosions. However, the concentrations and crystal structures detected on 3I Atlas matched industrial specifications rather than natural cosmic abundances. The spectroscopic signatures revealed nickel alloys with compositions identical to materials used in terrestrial aerospace applications. These alloys require sophisticated metallurgical processes involving precise temperature control, controlled atmospheric conditions, and specific cooling rates that produce desired mechanical properties. Such materials exhibit superior corrosion resistance, structural strength, and thermal stability compared to naturally occurring metal mixtures found in meteorites and asteroids. What makes this discovery even more remarkable is the uniform distribution of these metals across the entire visible surface. Natural objects typically show patchy compositions where different materials got mixed together during formation, creating a mottled appearance when viewed through spectrometers. But 3 Atlas shows consistent metallic signatures no matter which part of its surface reflects light toward Earth. This uniformity suggests either a coating process that covered the entire object or manufacturing techniques that produced homogeneous material properties throughout its structure. The preservation of these metallic characteristics also defies expectations for objects that have spent millions of years traveling through interstellar space. Cosmic radiation and micrometeorite impacts should have altered surface materials over such extended periods, creating the kind of weathered, oxidized layers we see on asteroids and meteorites. Instead, 3 Atlas exhibits the pristine signatures of recently processed metals as if it was manufactured within the last few decades rather than eons ago. Laboratory analysis of reflected light from 3I Atlas's surface showed crystal grain boundaries and stress patterns consistent with forging and heat treatment processes. X-ray diffraction spectroscopy revealed oriented crystal structures that form only when metals are worked under controlled conditions. then subjected to specific thermal cycling to optimize strength and durability. These characteristics never occur in naturally formed metal deposits, which cool randomly in space and exhibit chaotic crystal arrangements. If 3I Atlas contains artificially processed metals, then some intelligence must have created those materials using advanced technology. The durability required for interstellar travel across potentially millions of years suggests manufacturing capabilities and quality control that exceed current human industrial standards. These materials would need to resist cosmic radiation, micrometeorite bombardment, thermal cycling, and chemical degradation across timescales that dwarf human technological development. The gas cloud that shouldn't be there. The James Webb Space Telescope detected a massive bubble of carbon dioxide gas surrounding the object, stretching out for about 350,000 kilometers in every direction. To put that in perspective, you could fit the entire distance from Earth to the Moon inside this gas cloud and still have room left over. This discovery created immediate problems for anyone trying to explain 3I Atlas as a normal comet. The gas cloud is way too big to exist naturally in space. Think of it this way: when you spray a garden hose, the water doesn't keep spreading forever. Solar wind acts like a constant cosmic breath that should push gas molecules away from comets and compress them into much smaller areas. The fact that this enormous gas bubble exists at all suggests something is actively maintaining it, almost like an invisible barrier keeping the gas from dispersing the way it should. The gas composition itself raises additional questions about what's happening inside 3 Atlas. Most comets release water vapor as their primary gas component because water ice makes up the majority of their frozen material. But 3 Atlas produces mostly carbon dioxide, which requires different temperature and pressure conditions to sublimate. This suggests either unusual internal composition or active processes that selectively generate carbon dioxide while leaving other materials unchanged. Temperature measurements of the gas cloud reveal another impossibility. The carbon dioxide maintains consistent temperatures throughout its enormous volume, from the surface of 3-2 Atlas all the way out to the cloud's outer edges. Natural gas expansion in space should create temperature gradients as molecules spread out and cool down. But this gas cloud shows uniform thermal characteristics that suggest active heating mechanisms maintaining specific temperature distributions across hundreds of thousands of kilometers. Even stranger, the gas molecules inside this cloud are moving faster than they should be able to escape from an object the size of 3I Atlas. It's like watching someone throw a baseball harder than their arm strength should allow. The speeds these molecules are traveling suggest either that 3 Atlas has much more mass than we can see or something is actively accelerating the gas after it escapes from the surface. Neither explanation makes sense for a natural chunk of ice and rock. The energy math doesn't work either. Scientists calculated how much solar energy reaches 3I Atlas at its current distance from the Sun, then figured out how much energy would be needed to boil off enough carbon dioxide to create and maintain such a massive gas cloud. The numbers are off by about a factor of 100. It's like trying to boil a swimming pool with a birthday candle. There simply isn't enough energy available from sunlight alone to power what we're seeing, which means something else must be generating this gas through processes we don't understand. The impossible navigation. Here's where 3 Atlas gets really unsettling. This object, which supposedly drifted in from another star system across distances so vast that light takes years to cross them, is heading toward Mars with the precision of a GPS-guided missile. The level of accuracy required to achieve this kind of targeting from interstellar space is so extreme that calling it a coincidence stretches the definition of the word beyond any reasonable meaning. Imagine trying to hit a marble with a pebble thrown from the next state over, except both the marble and the pebble are moving at thousands of miles per hour in different directions, and you have to account for the gravitational pull of dozens of other objects along the way. That's essentially what would be required for a random chunk of space debris to naturally end up on a collision course with Mars. The mathematical odds are so small that astronomers use terms like statistically impossible when discussing them in professional journals. The approach vector analysis reveals another disturbing detail about the trajectory precision. When astronomers trace the path of 3 Atlas backward through space, it doesn't point toward any known star system within a reasonable travel time. Most interstellar objects show clear origin points that align with nearby stellar neighborhoods where they could have been ejected by gravitational interactions. But 3 Atlas appears to have come from empty space between star systems, as if it began its journey from nowhere in particular. The velocity profile also doesn't match what you'd expect from natural gravitational ejection processes. When planets or stars fling objects into interstellar space, those objects carry specific energy signatures that reflect their escape mechanisms. Rocky materials get ejected at different speeds than icy materials, and the size of the object affects how much velocity it can achieve during ejection. But 3.2 Atlas shows velocity characteristics that don't fit any known ejection scenario, suggesting either exotic formation processes or artificial acceleration during its interstellar journey. What makes this even more disturbing is that relatively small adjustments to the trajectory could turn a close flyby into a direct impact. Natural comets can't make these kinds of course corrections because they don't have engines or guidance systems. But if 3I Atlas could somehow change its speed by just 10 to 15 kilometers per second, it would go from missing Mars to hitting it dead center. That might not sound like much, but it represents more thrust than any natural process could provide and exactly the kind of precision maneuvering you'd expect from an advanced spacecraft. The trajectory also shows none of the random wobbles and perturbations that should occur when an object travels through the gravitational influences of our outer planets. Jupiter and Saturn are massive enough to deflect incoming objects, yet 3 Atlas has maintained its course with the steadiness of something that knows exactly where it's going. This kind of navigational stability suggests either impossible luck or active course correction systems that compensate for gravitational disturbances in real time.